That's our cue. All right, let's get started. So today we're continuing our conversation about HTTP. This should be up to date, right? I meant to download this before. All right. Okay. So let's talk about encoding. So the idea, I'll talk about it briefly. So the idea is I got some code running, which actually I can give more details in this than I can in 1.16. But it's running as a browser extension to start and stop the music automatically. So it should start at 4:48, and if it doesn't, you're going to hear me muttering about Spotify and complaining about it. So it should start at 4:48. That's my cue to shut up and put on the lecture question. I have a tendency to go over, and then I'm putting on the lecture question like 4:50 or 4:51. The music is going to cut me off, and then make sure I don't go over so y'all can get out of here on time. And then just plays until the next lecture. Because I have this room for 4 lectures in a row, so I get to do things like this. Today we want to talk about encodings. Let's just talk about them. So we mentioned how the internet works. We talked about not hash maps, not array lists. My brain has to catch up. I just did 3 hours of 1.16. We talked about IP and TCP. And whenever we send something over the internet, it's physical copper cables with high voltage, low voltage. It's fiber optic, light, no light. It's wavelengths that can send ones and zeros. It's all just ones and zeros. Everything is just ones and zeros according to the internet, according to IP, according to the routers of the internet. And it's up to us to make sense of those ones and zeros. But all we can do is send an IP packet of ones and zeros in the header, and then the content of that packet is just a bunch of ones and zeros, which are going to, I think I'm getting ahead of my slide here. No, I'm not. And the start of those ones and zeros will be the TCP headers, and TCP specifies send ones and zeros in this order, and we'll make sense of them like this. And then after that, the content, after TCP reassembles all our packets, it's still just ones and zeros that we're communicating with our clients. So somebody opens up a browser, punches in our URL, and sends a request to our server. That comes as just ones and zeros. Now, we saw last time it's an HTTP request with a request line, some headers, and potentially a body if it's a post request. And we talked about the new line characters, the /r/n, the CRLF. But how do we even get to that point? That's what we want to talk about today. How do we even get to that point, and how do we send different types of information? So to answer that second part, we're going to use MIME types. This is going to specify the type of content that we're sending. So the MIME type is going to say, hey, I'm sending you these ones and zeros, and this is how they're encoded. This is what we're actually sending, is the MIME type. This is going to be set in the content type header. So last time we mentioned content type header has to exist. And in the one example I showed with content type, it was text/plain. That's our MIME type, and that's the MIME type for, just as the name implies, just plain text. So MIME type consists of 2 different parts, a type and a subtype. It's separated by a slash. MIME, I always have to read this because I forget what it stands for. Multi-purpose Internet Mail Extensions. But it was so useful that it expanded outside of just mail, just outside of just email, and was adopted by HTTP at large and is used in many different contexts now. But we kept the name MIME type, still is part of the type. Some common types, text, which we already saw, and we're going to use this a lot up through Objective 2. Text is going to be your type with different subtypes. We're going to have text, image. When you get to Objective 3, you're going to serve images. So your type would be image, of course. And if you want to send videos, video is another common type. You want to serve an MP4 from your server, your type would be video for that. And then there's different subtypes as well. The 4 that you'll use for objectives 1 and 2, text/plain, text/HTML, text/CSS, text/JavaScript. These are all text-based formats. So HTML is just text. You want to write HTML, you open up a text editor. You're typing text, and you're sending text. So your HTML is saved as a file, but when you read that file, you're interpreting that content as text. You're sending text, text/HTML. When you get to objective 3, you will have image, image/JPEG, image/PNG, a couple image types. If you have different formats, you have SVG, image/SVG, etc. Whatever image type you have, get the right MIME type for that image. And if you want to send an MP4, like I said in the previous slide, video/MP4 would be your whole thing. Video/AVI, whatever your format is for your video. And this MIME type is going to tell the browser, this is how you interpret my 1s and 0s. This is how you're going to do it. I got a whole bunch of 1s and 0s here, and it's an MP4 video. Your browser is going to pull up its MP4 spec, and it's going to interpret those bytes according to the standard, according to MP4. If it's a JPEG, etc., it's just going to interpret them as whatever it needs to be. If it's text/HTML, it knows that it's going to read it as text and then interpret that text as HTML. So this is telling your browser, telling your user's browser how to interpret the data that you just sent them. Like I said, this goes in your content type header, and sometimes you want to specify additional information in addition to the content type. And right from objective 2, this will be important. We want to specify the char set for our text type. So we'll have a header context type, text HTML, for example, or text JavaScript. And then if we want to specify the character set, we're going to have a semicolon and then a key value pair setting the char set equal to UTF-8, char set, all lowercase, equals UTF-8, all lowercase, dash, not underscore, 8, and that's going to set the char set. Every character here has to be exact. I say the underscore specifically. I had a student in office hours pulling their hair out. They were hours chasing down this bug. They show me their code, and I'm like, bruh, underscore, that should be a dash. They replaced that one character, and it worked fine. And they were happy to be relieved to be done with it, but they were upset that that was the issue. So dash, not underscore. That has to be exact, all lowercase with a dash. So this is going to say use the UTF-8 encoding for this text. The sample site for homework 1 that you'll use for objective 2, for learning objective 2, that is, I already called the image objective 3. Application objective 1 for the image. For learning objective 2, the HTML and the JavaScript both contain a UTF-8 character, so you do need to set your char set to UTF-8. They purposely include that character to make sure that you know how to do this. So make sure you tell your browser, hey, it's text, but use the UTF-8 encoding. Your browsers are very sophisticated pieces of software these days. Your browser will, what we call, sniff out the MIME type. You send some data, maybe you have the wrong MIME type, maybe you didn't put a MIME type at all. The browser is going to look at the content that you sent, look at those bytes, look at those 1s and 0s, and say, this looks like HTML. And it's going to just say, I think this is HTML. I'm going to set the MIME type to text/HTML. Very sophisticated software that can basically figure out, based on the content, what you have. So it'll help us out with this. But the best practice is to say, hey, browser, we got this. Just back off. Don't sniff out my MIME types. I got my MIME types right. Just use the MIME types that I'm sending you. So we can disable this by adding an extra header, and this is required for the homework. X content type options, all uppercase letters, starting with uppercase letters for each word. No sniff. This says, hey, browser, do not use MIME type sniffing. Thanks for the help and all, but we got this. Best practice is to disable this. If you go to pretty much any website and look at the headers, you're almost always going to see a header like this. This should be set, in my opinion, should be set on every response. disable this MIME type sniffing and just get your MIME types right. If you have the right MIME type and disable sniffing, then you don't need that sniffing. You only need the MIME type sniffing if you made a mistake in your MIME type. Which is like, okay, well, maybe I just want to make mistakes and let the browser cover for me, which is fair. The problem with this, the concern is, say, like for homework 2, you're going to build a server where users can upload images, and then those images are served to all of your other users. So you have an upload button where your users upload a file, and you want them to upload images and share their images of cats and stuff, and just enjoy your app. Well, some smart user says, that doesn't work in that context. I'm like, I don't want to say ass in lecture. Some smart-ass user is going to say, well, I'm not going to upload an image. I'm going to upload some JavaScript that attacks other users, tries to steal their cookies and just breaks their stuff, or whatever they want to do, whatever malicious thing they want. So instead of an image, they upload JavaScript. You host that JavaScript as an image to all your users, what you think is an image to all your users. Browser takes a look at it and says, MIME type image/PNG, this looks like JavaScript. And it says, I think I'll just run this as JavaScript because this sure looks like JavaScript. It sniffs out the MIME type. It says, you got the wrong MIME type, bro. And sniffs out the MIME type of JavaScript, and all of a sudden all your users are hacked. Now in this specific context, hopefully you have that content in an image tag and the browser gets confused enough that it doesn't try to run it. But a sophisticated enough user might be able to get this in there to be able to get that JavaScript ran. But if you got MIME type image/PNG, X content type no sniff, browser's going to look at it and be like, it's not an image, and not do anything with it. And that's what we want. We don't want to open up security vulnerabilities where users can upload a type that we didn't expect and have that type served to all our users, and then have all our users be attacked by another user, by a malicious user. And probably not actually a user, probably somebody who says, oh, I'm going to try to break this site that I don't even use. Probably going to be a hacker like that. Disable sniffing, don't have to worry about that attack. This is our first, comes pretty early in the semester, but our very first of many security vulnerability that we're going to not put into our apps to make sure we don't have that vulnerability. So when we send any response, besides 301 where you don't have any body, but if you send a response that has a body, it has some content, you have to have your content type along with your content length. But your content type and content length that we mentioned last time, your content type has to have the correct MIME type. Add a character set, character encoding, if necessary, for your text especially. Text should have your character encoding, which is, for our purposes, UTF-8, always in this course. And then content length we'll talk about in a bit. We're not quite ready to talk about that yet. And whenever you're receiving a request that has a body, this is going to be our post request. That post request will also contain a content type telling you how to parse that content. And to be honest, for this class, if you have a specific path, the homework says, make a path and accept requests with this stuff, you can just assume the content type. You can read it and parse it and check the content type, but the content type should just be whatever you expect the user to send you at that path. And then if it's not, I think in all the assignments, if it's not, we're just not going to test for that. We're going to test with valid inputs for the most part. Okay, but we talked about text quite a bit. We got plain text, HTML, CSS, JavaScript. These are all text encodings, and I said, just slap charset UTF-8 on top of that bad boy, and it's good. But let's talk about these encodings and talk about what UTF-8 even is. Actually, let me pause for a sec. I feel like I'm just marathoning. Any questions so far? You have to have your content type that contains your MIME type and any additional encodings. Don't let your browser sniff MIME types. Yeah?
Does the order of content length
No.
and content type matter?
Mm-mm. So the question, does the order of content type and content length matter? No. And in general, the order of the headers doesn't matter. The headers are going to are effectively a big key value store where order, they can be treated in any order. Oh, that was in chat. How come you saw that before me? Is my phone slow? I was watching chat, and I swear that wasn't there when you asked, when you read that. But no, in general, the order of headers does not matter. As long as all the headers that you need are there in any order, it's fine. The way you're going to parse headers and the way browsers parse your headers, you parse them all, put them all, if you follow my recommendations anyway, which I'll say throughout the semester, parse them all and throw them all in a key value store. If you're using Python, throw them all in a big dictionary. And the dictionary doesn't, or most key value stores in most languages, don't preserve your order anyway. It's just a key value store. Give me the value at this key. So the order's not going to matter. Okay, we just got ones and zeros. How do we send text? A lot of what we're doing is text. How do we send that text? How do we receive that text in a way that is going to be allowed over the internet? Internet can only ever communicate in ones and zeros. I want to communicate in letters and characters. How are we going to do that? Well, ASCII to the rescue. ASCII is an encoding, a 7-bit encoding that encodes characters to different numerical values. Here's your entire ASCII chart, and then those numerical values can be broken down into their bytes, their ones and zeros, and then shoot those ones and zeros over the internet. So, for example, if I want to send capital P that has ASCII code 80, which in hex is 50, so I'm going to have 0, well, it's a 7-bit encoding, so I start with the 101, 0000. I'm going to send those ones and zeros. I'm going to say, hey, I'm using ASCII. And then the browser on the other side is going to say, oh, that's capital P in ASCII. And that's how we send characters. Fairly straightforward. Just every character has a 7-bit encoding. And we just use that encoding and say, hey, this is ASCII. I'm using this encoding. Here's a bunch of ones and zeros. Look up your ASCII table and interpret these as characters. Problem solved. We're done. We can communicate text over the internet. But Jesse, you said UTF-8 earlier. Oh, yeah. Okay. So ASCII is fine. If we're going to send the string, say hello. We're going to look up our chart. Well, we're not actually going to, but we're going to put ASCII in there and tell Python to take care of it all for us, or whatever language you want to use. But the string hello is going to be language specific. In Java, we have a string. In Python, we have str. In JavaScript, it's str. I shouldn't have even started that sentence. But we have a language-specific representation for a string, which is going to be different in every single language, just the way that they store the string. Is it an object? Is it, what's going on with this thing? So we want to encode that using ASCII and convert it to bytes. We convert this to a 5-byte sequence, a byte array, and then send this over the internet, which in binary, hello, is going to look exactly like this. That's what's sent over the internet. That's how we communicate with text, just by using these encodings to encode our characters. Very important concept. It lets us communicate text over the internet. HTTP headers. So the reason we're even talking about ASCII, well, one of the reasons, I would probably talk about it anyway, but HTTP headers are ASCII only, including the request and response line, the request and status lines. ASCII only in HTTP headers. ASCII only. So the characters on that chart, these are the only characters allowed in your HTTP headers. That's it. Nothing else. Nothing else is allowed. The body of a post request and the body of your responses can contain any content you want. That's where we use content type, specify the character encoding, and then whatever the encoding is, and then put whatever we want in the body with any encoding available to us ever. Headers, only ASCII. It's just the standard's pretty old. Like it came around in a long time ago. So we're kind of stuck with this relic from the past, ASCII only. The request line includes the path. So this does imply that URLs, the path of a URL, the query strings, the fragments, ASCII only in any of that. And you've never seen a non-ASCII character in a URL. Can't happen. Can't do it. Just can't do it. Which, okay, we can communicate text, but ASCII is 7-bit. It's a 7-bit encoding. It's only 128 different values. This is okay for English text. Even then, it's not perfect. But, we have all our uppercase, all our lowercase letters, our numbers, our special characters. We have all those characters. We can get by with ASCII in English. But what if we're using a language that doesn't use our English alphabet? Then we're just completely out to lunch. We can't use ASCII for that. So there's a few solutions that we could have. One, just have a different encoding for every language that uses a different alphabet. Well, that's a pain. The internet is global right now. Obviously, I say that as if I'm revealing information there. But the internet's global. So having different encodings for every language, every different alphabet, that would be way too cumbersome. It would be really inconvenient, I'll say, for the internet. We'd have to write a lot of code to handle different encodings. So the better solution, and one of the situations in programming and software engineering where somebody proposed a good answer and everybody just went with it. And we just have one answer, and it's fantastic. That answer is UTF-8. There's also, I say one answer, but there's also UTF-16. There's a couple different UTFs. UTF-8 is the one that really took off. And this just has everything. Like every character, every alphabet, everything in just one encoding. Emojis, it's all in UTF-8. So we just encode everything in UTF-8, and that's it. One standard to rule them all. It's fantastic. Instead of getting into a new space, and it's like, well, here are your options. I want to do ORMs, object relation management. Here's 50 different options. There's no standard. Pick one. And you got to weigh pros and cons and do a week of research to figure out which one to choose. This is one case where we don't have to do that, thankfully. You just use UTF-8 for your character encodings, end of story. So what is UTF-8? Well, first, ASCII is a subset of UTF-8. So everything we just said about ASCII, perfectly valid for UTF-8. Every character encoded using ASCII is also a valid character encoded with UTF-8. If you take ASCII text and encode it with UTF-8, it's identical to that text encoded as ASCII. ASCII is a subset of UTF-8. So everything that's in ASCII, including our HTTP headers, perfectly valid UTF-8. So very convenient right off the bat. So if a byte starts with a 0, thankfully ASCII is 7 bits. So if it starts with a 0, the remaining 7 bits are ASCII, is the ASCII equivalent. Very convenient. If we need more bytes, UTF-8 is an up to 4 byte encoding. If we need more bytes, we're going to have the first byte of that character start with a number of 1s equal to the total number of bytes. So if I have a 2-byte character, I need 2 bytes to represent this character. I'm going to start with 1, 1, and 0. So I start with 2 leading 1s, and that means this and the following byte both encode the same single character. And then the next byte is going to be a continuation byte. All continuation bytes start with a single 1. So if I need 4 bytes, 4 1s, then a 0, and then 3 continuation bytes. There's a few reasons for this encoding. The biggest one, in my opinion at least, is that no character is a subsequence of another character. So it makes decoding easier. It makes identifying decoding errors easier. If a bit is flipped or anything, it's easy to detect those errors and say, hey, this isn't valid UTF-8. This also means that if you take any random bytes, let's say the bytes representing an image, and try to treat them as UTF-8, it's not going to be valid UTF-8. You'll hear me talk about that at length today. Starting later today, but at length throughout the semester. So that's UTF-8, up to 4 bytes encoding, which means we can encode lots of characters. I don't have a number off the top of my head, but lots of characters. Every alphabet, every languages that use a different character for every word, it's all in here. There's enough bytes to represent all of that. It's all in here. So we want to send strings over the internet. We have a language-specific string, and we need to convert it, encode it using UTF-8. We encode the string into a byte array, encode it as UTF-8, and then send the bytes over the internet. That's our ones and zeros as bytes. When we use our TCP socket libraries, any language that you're using, it's going to be byte arrays. You're going to read an array of bytes, and you're going to send an array of bytes. Or maybe not always an array, but a sequential data structure of bytes received and sent. So that's what we need. If we have a language-specific string, then we need to convert it into a sequence of bytes and then send that over our TCP socket. Yeah, I just saw that there's stuff in chat.
How do we express like
I was going to say we don't, but let me give you a more thorough answer. So the question is, how do we express fonts in here? So the text itself doesn't inherently have any font applied to it. It's just the raw text. And then if we want to add font to it, it would be in our CSS or our HTML if you're afraid of CSS. And then you would specify the font in your CSS. And then when the browser goes to render the text, it would take the raw text, look at your CSS. Your CSS says, oh, make this Arial. And then it'll apply that font to the text. So the text and the styling are kept separate. I can't even read that number. 1,000 million, 4.3 billion. It's enough. It's enough. Of course, the UTF-16 does exist, so somebody decided that wasn't enough, apparently. When we receive bytes over the internet, so we have our TCP socket and we say, give me some bytes. We're going to receive that as a sequence of bytes, and then we need to decode it into our language-specific string. So we're going to decode it with the proper encoding, in our case UTF-8 for everything, and then get it in our language-specific string and then work with it. If you've worked in Python and you've done anything related to this, maybe even if it wasn't web development, anywhere where you've had to do .decode, .encode on your strings and byte arrays, this is what you're doing. When you have your Python string, your str, and you do .encode, you're converting it to a sequence of bytes encoded using UTF-8. UTF-8 is the default for Python these days, so you don't have to specify your encoding. It'll default to UTF-8. .encode converts your Python string to a sequence of bytes using UTF-8. If you have a bunch of UTF-8 bytes, you hit it with a .decode, and it's going to convert it to a Python str string. So encode and decode, if you ever worked with this and you chase a bug and the internet says, oh, you forgot to do .decode. And it's like, why do I have to do that? This is why. It's converting between language-specific and sequence of bytes encoded using UTF-8. Which you will have to do. So like I said, you read from the TCP socket, you get a sequence of bytes. If you hit it with the .decode, you're going to get your string, and then you can do all your string parsing if you're allergic to byte parsing, which if you are, that's fine for homework 1, but when you get to homework 2, byte parsing is where it's at. Homework 1 is the string parsing homework. Homework 2 is the byte parsing homework. Homework 3 is the bit parsing homework. Effectively, it's just kind of coincidentally how it ends up in this course. And then homework 4, I guess we go back to strings. So you get those bytes, you decode them into a string, and then when you want to send anything over the TCP socket, you encode your string and then send it. Yeah.
Where is the socket information held?
Oh, that question might be over my head. So where's the socket information stored? Is it?
Before Python gets the stream, where is that buffer stored?
I don't know. So the question is, where is the buffer stored before Python gets the data? I believe, I'm going to guess, but I don't know 100%, so don't take this as ground truth. But I believe it's stored in Python. Like the socket server library will have all the functionality to get the bytes from the operating system, and it'll store it in its own buffer, waiting for us to ask for that information. And once we ask for it with our receive method, then it'll get it from wherever it's stored in the socket server code. That's my understanding, just kind of in my head canon, that's how it works. So if that's wrong and you look it up, please let me know. Yeah, no problem. So if you don't encode after request, the page will not get anything then. If you don't encode when you're sending your string over the internet, you'll have an error in your server. Your server will crash when you try to send that. Because you're calling a method that takes a byte array and you're giving it a string, and you're going to get expected byte array, found string, type mismatch, crash. So the browser won't even see that error. They won't even see a 500 unless you're catching the exception. Your browser won't even see the 500 because the server just crashed. So the browser will just hang, waiting for the response that it's never going to get. Your content length is the number of bytes in the body of your response. And for post request, it's the number of bytes in the body of the request. Your content length is the number of bytes in the body of your response. So in the first example on Friday, I sent the text hello, and I said content length 5, easy. Hello, lowercase h, ELLO, all ASCII characters. ASCII characters are all encoded with 1 byte. So if I took the string hello and did dot length and set that equal to my content length, I would get away with that. It'd be fine. But what happens when you have a non-ASCII character? When you have one of these characters that takes multiple bytes, you cannot take the length of the string and use that as your content length. It will not work. It will not work. Make sure you're getting the number of bytes for the content that you're sending, not the length of the string. So if you have some non-ASCII characters, you got a bunch of fancy UTF-8 in here, you got some non-English text, you're getting a lot of bytes per character. Maybe you have 2, 3, and 4 bytes per character for a lot of those characters, and you're sending over the internet. Make sure you get the number of bytes, not the length of the string. If you set content length to the length of the string, or in general, if you set the content length equal to a value less than the number of bytes that you're sending, the browser will hold you to that, and it will only read that many bytes. So if you have 200 bytes of data in your HTML, and you say content length is 100, well, the browser's going to read 100 bytes and be done with it. Throw away the other 100, and then your user's only going to get half of your HTML. And that's what's going to be rendered to the page. So if you have a lot of UTF, a lot of non-ASCII UTF-8, and you're taking the length of the string, you're missing content. Your users aren't getting all of the content that they asked for, that they requested. You have to make sure this is the length of, is the number of bytes, not the length of the string, the length of the byte array. Now you can do this if you're using Python. If in encode, you encode your string as UTF-8. That gives you a byte array. Then just hit that with len. Len of the byte array after you encode it into a byte array. Then you're getting the length, you're getting the number of bytes, the length of the byte array. Don't get the length for the content length before you encode into UTF-8, into a byte array of UTF-8. Content length is not the length of your string. This used to be a very, very big problem, a common problem in this class, lots of office hours and lots of Piazza questions and stuff. I emphasize this enough in this lecture that I don't see that issue much anymore. Don't be the person that's taking length of the string as content length. Don't do it. Just don't do it. Okay. Any questions so far? See the syllabus for more info. Oh, there's a good question in here. I'll say yes. Are we allowed to use a library to get the size in bytes of a file, like FS in JavaScript? Yeah, I'd say yes. In general, if I show you very specifically how to do something in lecture, then I want you to do that thing in the code with all those details. If I don't show in detail something in lecture, then you're free to use the tools available to you to get that job done. I never showed you how to get the number of bytes, like the size of a file. So if you want to use a library for that, I'd be fine with that. But in general, the way I would expect you to get the bytes, the length, the size of a file is read the entire file into memory, and then len, whatever byte array you read it into. That would be the way I would expect you all to do it. But if you want to read it before opening the file, using some fancy stuff, go for it. Yeah, the content, I had to rush that at the end of last lecture, but for a redirect specifically for your 301 in Learning Objective 1, the content, there is no body to the response. It's the only response you'll send without any content. That's a misspeak. There is one other one in Application Objective 3. But when there's a response with no content, you should be able to just leave off content length, just have it omitted. The spec says, the HTTP spec, the RFC says, if there's no content length, assume a content length of 0. The browser's supposed to implement that. With 301 specifically, we all have issues with Firefox. Without a content length, Firefox will just hang and it won't redirect. Like it's expecting to read some bytes of the body and the bytes aren't there and it just hangs. It's consistent. I see it whenever I do it. When I do my solutions, I see it in office hours. Students will have the issue. But if you add content length of 0, that appeases Firefox. It stops expecting any content to be sent, and it follows the redirect properly. I maintain that you shouldn't have to do that. I believe it's a Firefox bug, but I can't find, I searched the internet so long and far, trying to find any documentation of this bug, and it's not out there. It might be up to me to get it out there. But if you ever find information about that, I've been thinking I should put a bounty on this. If anybody can find out why that is the case, I don't know. What do you want? What would incentivize you? Just cash, I guess. But if anybody finds the answer to that, why that is the case, I would love to solve that mystery once and for all. But for now, until that's resolved, your 301s just put a content length of 0 to appease Firefox. I didn't say the other side of this. Thanks, Argo. So if content length is more than the amount of content that you send, the browser just hangs. If you send 50 bytes of data and you put content length 51, the browser's going to wait for that last byte. And if it doesn't get it, the user doesn't see any content. So that's definitely the worst case, a case that's worse than too low of a content length. Too high of a content length, and everything just hangs. So is the content length only for a message written within the request itself? I'm not sure how to interpret it, but I'll give you a general answer. Content length is for any request or response that has a body. If there's any information after the headers, you have to have content length and content type. So whether it's a post request coming from your users or a response that you're sending to your users, if there's a body, there's a content length and a content type. And if it's Firefox, there's a content length anyway, even if there's no content type. You're welcome. So when you get to Learning Objective, Application Objective 1, so the third overall objective, you have to send a message. And we're ripping through this homework, by the way. This is, after today, everything Learning Objective 1, Learning Objective 2, Application Objective 1. There's nothing holding you back from doing all of that after today's lecture. You're armed with everything you need to know. for any of that. If you're not feeling up for that, you don't feel prepared for that, hit me with the questions so I can help you out. With the exception of Docker, you can't set up Docker and Docker Compose because I haven't said anything about those yet. But we will have lectures. That is Wednesday, right? It should be Wednesday, Friday, and Monday. We got a lot of Docker in our near future. So let's talk about application objective 1, sending images. The most important thing to remember about sending I can't even say that because the most important thing, not the one I was going to say, I'll say that second. Most important thing about sending images are not text. Never, ever, ever encode your image. It'll break everything. The next most important thing, which I was going to say was the most important thing, don't overthink images. Sending images over the internet is super simple. It's easier than sending text. Just don't overthink sending images. So image, your general strategy for sending an image is read the bytes of the file. A file is just a sequence of bytes. Read it. Make sure you're reading it in byte mode. Don't read it as text because it's not text, it's an image. Read the bytes of the file, and that's your byte array. You're already done. You're already at the step of after you formatted your text response and encoded it into a byte array, you're already at that point. You're ready to get its length. That's the content length. You append it to the end of after your headers, after that new line, and ship it. Set your content length, content type. That's it. You do less for sending an image than you do for sending text. For example, with HTML, like you're reading your HTML file and building a response and everything with that, you're doing less work when you're sending an image rather than text. The image is not encoded with UTF-8. It's going to be encoded with, for our purposes, JPEG, the JPEG encoding. JPEG, it's a format, it's a file format that says the bytes will be in this order, they'll mean these things, there will be headers, then the content and everything. None of that is going to follow UTF-8. It's not going to follow the format of either a byte starts with a 0 or it starts with a number of ones, and then the number of ones there, that number of bytes are going to, -1 will start with 1, 0. Like, it's not going to follow that format at all. So if you try to take an image, which are just going to have a bunch of random, not literally random, but random 1s and 0s, and try to decode it as a string, taking this byte array and decode it as a string, it's not going to work. You're going to get all kinds of encoding errors, or even worse, you'll just silently get logical errors. So hopefully the program just crashes and says, yo, you can't do that. What are you doing? Fix your shit. Or it tries to decode it and just gives you random garbage text, and then when you try to re-encode it, you don't get the same image that you started with because it tried to decode into valid UTF-8, and when you encode that back, you don't get back to the same bytes. You can't get back to the same bytes. You take an image, convert it to a string, and then convert it back to bytes, you don't get the same bytes. It will not be the same bytes. Do not ever convert your image into a string. It will corrupt your image 100% of the time. I'll say, no, I'm going to say 100% of the time. It would have to be pure cosmic luck that your image actually could be interpreted as valid UTF-8. It's phenomenally unlikely. Don't do it. So, and this is important when you're reading the image. If you just do with open file name in Python, the default is to open that as a string. Whenever you've opened files before, 115, 116, whatever class you open strings in, your side projects and everything, you almost always wanted to read it as a string. You're reading a CSV file, you just want to read it as a string, and you didn't have to do anything special to say, this is UTF-8, it's a string. You just open the file and it treats it as a string. So you do have to do a little bit extra here to make sure that the file is read in byte mode. In Python, you open the file name, give it another parameter, and say, B, I want to open this in byte mode. And then it'll just read the bytes and not convert it to a string. Like I said, don't overthink these. Files already in bytes, that's what you want. We do extra work to encode our strings as bytes. We read the file in bytes, and it's already in bytes. Length, len, get the length of it, done. Send it. So let's demo a couple things that we just talked about. Visual Studio Code. So let's stop this server. It's still running from last time. So let's make a little more sense out of the stuff that we saw last time. When we received information from the server, we saw we got our request. Oh, that's a bad example. We saw we got our request line. This is a get request for the root path. I didn't specify any path, so we got the default root path of /. I have some headers here, which will include topic for another day, I guess, but my user agent, which has identifying information about me, a little bit of identifying information. This has what browser I'm using, what operating system I'm using, and some other information about me. You ever notice you go to a download site, and whatever operating system you have, it just takes you immediately to the download page for that operating system? Well, you're not just using the most popular operating system. I mean, you might be. But it read your MIME type and said, oh, it looks like you have a Mac. I'm going to take you to the Mac download page. So there is information that you're leaking right through this user agent. You're leaking information about you. If you really care about your privacy, you would want to hide that user agent and not send any information about yourself. Some other headers, not much interest in there. And then for this context. And then when we responded, we're going to respond with a 200 OK. Content length of 5, content type of text plain using UTF-8, and then my actual content of hello. And we saw this worked, we just rendered hello in the browser. If we change the content length to 3 and rerun this, we only get 3 characters. The browser is going to take our content length as pure gold, as ground truth. I said content length's 3. It said I'm reading 3 bytes, and that's it. I'm not reading any more than that. You said 3. I read 3. Likewise, I'm sending 5 characters in hello. I say content length is 6. The first case of this. I'm just going to change it. I don't have time to talk about that one, but we will. I'm going to change the port to 8001. And it hangs. It's never going to load. It's expecting that 6th byte. It's never going to get it. And it just sits here and hangs. Doesn't do anything. That content length has to be